First talk today will be the second talk of Mike Bell. If you want a more elaborate introduction.
That's fine.
Thank you.
Yeah. So again, the title here doesn't relate to anything that was on the internet. Okay. Let's get started. So, what did we do yesterday? I know it's been a long conference already.
Yes.
It's day 2. There were 6 talks yesterday. There's 7 today. So yesterday, what I talked about was I described what an n-infinity operad was. And I pointed out how n-infinity operads are the exact same data in sort of a higher categorical sense as a poset. And it's a really easy to describe combinatorial poset coming from either transfer systems or indexing systems, depending on how what you want to emphasize in your computation. And the other thing was that n-infinity operad's job is to parameterize twisted forms of a multiplication. So in this case, I can plug in not just a set with a trivial action t, but I could put in a set with a possibly non-trivial g or maybe some h action, and then I have a map back that is refining the multiplication. So the things I want to talk about today, potentially in this order, also potentially in a more organic order, depending on what shows up on the slides, is the first. How does it interact? What sort of coherence do I see between these? Because what I actually said was that I have these twisted multiplication maps, but I didn't spell out any structure that says that these are actually related to each other. That right now, as I framed it, you just have a bunch of maps. And I said, in fact, you have essentially a unique one for each admissible set. And so then the uniqueness endows this with a lot of internal coherence. And the second part, and that I want to actually focus more on, is what's the algebraic shadow of this entire story? Because I like to think that I'm actually an algebraist, but that wasn't the funny part. But nobody believes that. That was the funny part. So we get to different geometers too. We get to live out my image of algebra. So the thing I want to start with is again thinking about coefficient systems and sort of engaging with the Elmendorf style approach from last time.
Val's doing its thing.
I know, weird as hell. You thought you were going to have to edit today's. So when we talked last time about coefficient systems, these were just functors from the orbit category op into some category, like spaces, like sets, like whatever. One of the nice things about finite G sets is that every finite G set, in fact, an arbitrary G set, but it has a decomposition into orbits, into any G set can be written as a disjoint union of the orbits G mod H as H varies. And it's essentially up to reordering, it's unique. And one of the ways that I can frame that, since disjoint union is the coproduct, is that finite G sets are the finite coproduct completion of the orbit category. I just sort of formally put in coproducts of the basic building blocks. In fact, all G sets are the coproduct completion of the orbit category. And then another way to think about Elmendorf's theorem a la Duggar is that G spaces are the homotopy colimit completion of the orbit category. So it's all the same kind of idea. And to say it's the finite coproduct completion is to say that the functors, and then I put the little coproduct symbol there, that commute with coproducts out of finite G sets into some category C that admits coproducts are the same data as a functor from the orbit category into C. And this functor is just the restriction. There's an obvious inclusion of the orbit category into its coproduct completion, and I restrict along that. So because of that, I can rewrite what does it mean to be a coefficient system in that I had it as a functor from the orbit category op into some category like say set or top or whatever. And if I instead think of this as, well, I'm doing the orbit category op, so the finite G sets op is the finite product completion of the orbit category op. And so here I have product preserving functors out of finite G sets. Op into sets are the same thing as coefficient systems. Now it seems like I'm not buying anything from this added categorical manipulation. But one of the things that I'm going to get is that there are easier to understand manipulations between G sets than there are between orbits. And one of the simplest ones is if I restrict an orbit to a subgroup, it's not an orbit generically. I have, as Natalie pointed out, the double coset formula that exactly tells me how do I break up the restriction of an orbit into a distant unit of orbits. On the other hand, if I restrict a G set, that is an H set. And I don't have to worry about any of this. So it's the kind of thing where that category machinery is going to make a lot of my later computation much easier. The prototypical example that I want to keep in mind for all of this, that's the algebraic shadow of what I'm talking about, are the homotopy coefficient systems. If you give me a pointed G space, then I can talk about its homotopy groups, but they fit into this framework. And again, this is, all right, there. This, I don't want to do this. This is a product preserving functor because I'm mapping out of like a disjoint union, and then it's like, what's the definition of the coproduct? Yes, out of it are products. So it's a really, it's a pretty tight package. So here's the payoff for making this categorical switch, that finite G sets restrict to finite H sets, and oh damn, I did the wrong arrows. And so here I have an adjoint pair. The left adjoint is on the left, and that's induction, which takes me from H sets into G set, and the right adjoint is the restriction. There's also a further right adjoint to the restriction that's co-induction. I'll come back to that one later. It doesn't play a role in this part. Now, weirdly, when I'm talking about coefficient systems, so if I had coefficient systems in any category of finite products, then I can talk about coefficient systems for G, so product preserving functors out of bin G op into C, or coefficient systems for H, the same thing with an H everywhere. And the adjoint pair at the top gives me an adjoint pair below, but the roles of left and right are swapped because op. And so the left adjoint, which was the G mod H plus is the one that's giving me weirdly the restriction here. And then the right adjoint was the restriction, and that's giving me co-induction. So it's, again, something that I can just write down what the answer is, but it's a little confusing when you first see it. All right, so to make it a little more precise, I rendered this diagram. Yeah, thank you. It is really nice. I don't want to tell you how much of my life was consumed by this. But I will say it's time I'll never get back. So, yeah. Yeah. Anyway, here's what is the data of a CP coefficient system. I have two orbits for CP. I have CP mod E and I have CP mod CP. And then I have the endomorphisms of CP mod E is a copy of CP itself, acting on the right on CP mod E. And I indicated that with a little gamma for my choice of generator. And then I also have my map CP mod E down to CP mod CP. So when I opt everything, that gave me a map the other way that I'm calling the restriction from CP mod CP down to CP mod E. And because there's a unique CP mod CP is terminal, there's a unique map from CP mod E to it. In fact, this map here lands in the fixed points for the CP action here. I'm not going to indicate that, but that's the only condition that I have. Now the restriction functor, which took my CP coefficient system to just abelian groups, so H is the trivial group, that's just evaluate here. And forget that there was a CP action. And so the two adjoints to that, the one that I described last time is the right adjoint, last slide, is the right adjoint. And this is what it looks like. The underlying is just functions out of the group ring. So this is the representation theory co-induction with values in my abelian group, M of CP mod E. And then the fixed points, value at CP mod CP, is just M of CP mod E. And the map from the identity to the right adjoint composed of the left adjoint, so the unit of the adjunction, is kind of a categorification of the restriction that showed up in my coefficient system. That's why I called the map at the top also res, although I sort of put it in a different, I used a capital letter to indicate that it's sort of this Mackie version of it. There's also a left adjoint to the restriction functor. It's the one that I call induction. I'm never going to talk about it again. And part of the reason is it's the kind of thing where, like, one of the key ideas that we're going to see again and again over this talk and then the one on Thursday is that when I'm doing the G commutative monoids, then the right adjoint is the one that I want to keep focusing on, and it becomes the left adjoint on the G commutative monoids. It's the better behaved one. That 0 in the upper left-hand corner, I mean, on the one hand, it's really easy to map out a 0. On the other hand, it's too easy to map out a 0, so it doesn't really carry any information that's helpful. It tells me that there was 0. Okay, great, thanks. Kind of knew that. All right, so just keep this picture in mind. And the other thing I want you to keep in mind is the fact that I had this map from M to the right adjoint composed to the left, and that it was describing for me something about the underlying coefficient system M itself. So I can package all of this into one picture by saying, let me take my coefficient system and use the fact that finite G sets has an additional operation on it given by Cartesian product. And I can take my finite G sets and just cross it with an arbitrary fixed finite G set. Cartesian product distributes over disjoint union. And so if I had a product preserving functor M, then this new one that I built, S goes to M of T cross S, is again a product preserving functor from finite G sets in. This is contravariant in T as well as in S. So I can think about them as running the two variables separately. And so this gave me a different kind of diagram. Now it's one from finite G sets op into not abelian groups, but rather into G coefficient systems. And this is, again, this kind of externalization of the diagram that I started with. I had a diagram from Bingiop into AB. This is lifting that whole diagram into a diagram into coefficient systems. And the value at some orbit, because again, this functor is also product preserving, because Cartesian product distributes over disjoint union in the other slot too. So this is product preserving, and all you have to do is tell me what was the value on orbits, and the value on orbits is this really nice functor on the underlying additive category. It's this composite of the left adjoint. So when I talk about the algebra that I want to do, I want to think about this functor, but the part that I'm really going to care most about is the core here, not the full sort of coefficient system of coefficients. But before I get there, I want to just unpack the Oneida lemma a little, because when I took that diagram, then I can apply this to any of my maps between orbits. So I'm going to look at the map from G mod H to G mod G. Now, the automorphisms of G mod H as a G set is the file group. It's the normalizer in G of H mod H. And the map is actually given by right multiplication. You sort of splice in an element of the normalizer between the elements of the group and the coset. So because this looks like a right action, it's actually canonically the vial group op. But groups are always canonically there. And I hope Shveta is not watching this because I keep saying canonical. But this one is in fact given to me by God that I have inversion in a group, and so this one I feel comfortable calling canonical. There's a whole liturgical joke I could be making. But so I have the automorphisms of this, that's the Weyl group. And the map from G mod H to a point is equivariant for the Weyl group action. Now, when I had a contravariant functor out of this, that gave me a map from M sub point to M sub G mod H, using the language I had before. And then I'm going to evaluate that at a point. And that gave me M of point goes to M of G mod H. This is a natural map in coefficient systems by sort of a Yonede type argument. This has to be the restriction in this. So I'm seeing all of the structure maps that show up in my coefficient system. They're all reflected instead in this diagram, but it's a diagram of coefficient systems. You're probably wondering why I'm spending so much time rambling about this. If you actually try to compute, say, something like equivariant homology or equivariant cohomology out of a cell structure, and I want to remember that my homology and cohomology are actually naturally enriched in, say, Mackey functors or in coefficient systems. This is the structure I need to actually describe the maps in the cellular chain complex. It's exactly describing for me how do I compute the cellular boundary mapping cohomology in coefficient systems. It's exactly coming from this externalization of the restriction or the Weyl action. So it's something that like, I would feel remiss if I didn't sort of stress that this is like the way you actually can compute with everything. All right, but let's get back to what happened with the operatic algebras. So one of the things I said last time is that if I have an admissible set for my n-infinity operatic O, then I had a transfer for T. And the way I could think about this is, remember, this side, this is the value, if I evaluate this on some finite G set S, that's the pi k of the space of equivariant maps from T cross S into X. And if I rewrite that, that's the space of equivariant maps from S into the space of maps from T into X. This one was pi k of the space of equivariant maps from S into X. So this map is just do pi k of equivariant maps out of S into the maps from T into X back to X. So it's exactly the image in pi k of that transfer map that I described. So if I unpack this just for the example of CP, then this gave me a map from the underlying, the value at CP mod E, back to the fixed points. And if I trace through what the naturality of this told me, it was that it factored through the co-invariance, because again, I had a unique map from CP to a point. And then the restriction of this, so if I compose this with the map back to pi kx of CP mod E, then that composite is the trace. It's the sum over the elements of the group. Those are the defining features for the transfer in a Mackey functor. The first condition is essentially sort of an equivariance one, and the second, this restriction to the trace, is the double coset formula. So I get this more generally if I took infinitely many copies of the regular representation, or really if I had any representation in which every orbit type embeds, then the corresponding functor that I get on finite G sets and isomorphisms, so I said I was going to restrict to the core, the finite G sets and isomorphisms into coefficient systems, so T went to pi k of x sub T, that actually extended to a covariant functor from finite G sets into coefficient systems. I'd use that it was a contravariant functor. That's the part that every coefficient system automatically gave me. The surprising part, and the part that comes from this additional structure that the operatic algebra provides, is that I also have this covariant extension. And this is kind of the first real instantiation of the slogan that I made on the very first slide yesterday, that I have an external form for each of these. This is the external form for Mackey functors. It's a coefficient system together with this extension of my functor from fin G iso into coefficient systems all the way through fin G itself. And I want to play around with this a bunch. But before I do that, I want to say, well, what happens if I didn't have all of my transfers? And before I get to that, I really should probably define a Mackey functor, because I claimed this is the external form of a Mackey functor, and I've been dancing around this. So I'm going to start with the Linder category that I'm embarrassed to admit I used to call the Burnside category, but that's a misattribution, and so I was corrected, and so I'm trying to also set the record straight. So here, my category that I'm going to call script A for obviously Linder or Burnside is the category whose objects are finite G sets. And then the morphisms I have between any two are going to be isomorphism classes of correspondences. So sometimes called spans or roofs. And it's just a map from finite G set to both S and to T. And the isomorphism is isomorphisms over S and T. So you get a little sort of diagram, or a little diamond with an isomorphism. Composition here is by a pullback, and this is why I needed to be working with isomorphism classes of correspondences. Because of course, the pullback isn't sort of really even well defined. It's defined up to unique isomorphism. It's a limit construction. And so I run into this problem if I try to actually make pullback associative, that the pullback of a pullback isn't actually the pullback of the composite, it's naturally isomorphic to the pullback of the composite. So one of the fixes for this is to say, well, I'll just work with isomorphism classes and then don't worry. Another fix, and this is one that Barbara gives, and I hope will come up on Thursday, is to actually take seriously that I should consider all choices of pullback and build a higher categorical version where I just keep track of, as part of the data, what was the choice of pullback I was making at each stage. In the Linder category, the disjoint union of finite G sets is actually also the product. It stays the coproduct, but then in this case, it's also the product. And the maps that witness the sort of projections are built out of they're built out of the inclusions. If I had like S disjoint union, that's a terrible letter. If I had like, well, whatever, S disjoint union T, then I could either include S into T or T into T, and then the identity under the slot. And those are the two projection maps that witness S disjoint union T as the product. And so a Mackey functor for me is going to be a product preserving functor from this Linder category into set. And exactly as Natalie talked about yesterday, most people would actually at this point group complete. It's automatic that the value at any finite G set T is a commutative monoid. That's actually a property here that comes from the fact that once I knew that the disjoint union was both the coproduct and the product, it guaranteed that all of the Hom things were commutative monoids, and it actually guaranteed that all the objects themselves were a kind of commutative monoid, and so a product preserving functor necessarily had this feature, that M of T was always a commutative monoid. It also guaranteed that all my structure maps are maps of commutative monoids. So I have two kinds. I have ones that come from the, as Natalie said, the sort of backwards or wrong way maps. Those are my restrictions. And then I have maps that go in the expected direction, and those are my transfers. Those are all maps of commutative monoids too. So I get all of this structure for free. If you want, you can group complete the commutative monoids that show up here. That's not going to be a problem. And group completion, since everything's a map of commutative monoids, it always extends over the group completion. So here's an example. This one took so much less time to render for some reason. Very long rant about Tixie. But so here, if I'm doing just CP, again, I only have the two orbits that I have to consider, CP mod CP and CP mod E. I see embedded in this an underlying coefficient system, that was this part. And that came from the fact that finite G sets op embeds into the Linder category as a wide subcategory. It contains all of the objects, but not full. The maps that I'm missing are the forward direction maps. I just take those to be the identity. I also have a dual notion, a co-coefficient system, which some people call an efficient system. And if I'm ever refereeing a paper and you call it an efficient system, my report's going to start with several pages about that. So never call it that. It's a co-coefficient system because that obviously rolls off the tongue better. But I have the two pieces of data, and they're related by the double quotient formula, which in this case says that if I transferred up from here and then restricted back down, then it's the same thing as summing over the orbits. It's again the trace. It's just like what I saw when I had my external version, that if I took my trace, evaluated a point, and embedded and then restricted back down, it was just summing over the elements of the group. And the other feature is that that if I restrict and then do the group action, or I did the group action then transfer, it's the same thing as just doing restriction or transfer. I can think of this whole thing as saying the diagram is actually CP equinarium. And then the prototypical example, in fact, for any G are the representables. And if I do these in abelian groups, I'm going to group complete the commutative monoids I got by taking maps in the Linder category out of T into something. That's product preserving because maps into the product is in fact product preserving thing. That's the definition of the product. So works really well for us here. All right. So that story that I just finished telling really focused on the case that I had all possible transfers, and then I was rebuilding the acupunctures. So one of the things that Andrew and I started to wonder about is like, well, we're not seeing all possible transfers in most of these. In fact, I described, if I gave you little disks for a universe, you know exactly what transfers you see. You see the ones that correspond to those H sets that embed into my universe. So if I chose my universe sort of willy-nilly, well, actually for like CP to the N, it's like weirdly easy to get all of the transfers, but for most things, you'll end up missing a bunch. And so you get things where I'm not expecting to see all possible transfers. I'm going to see only some of them. This led us to this notion where, okay, how do I describe that in a way that's analogous to how Linder described an ordinary acupuncture? And the algebraic structure that we came up with is this. We call an indexing category because it's the sort of category version of the indexing system. And here it's a wide subcategory. That means it contains all the objects. Again, some category theorists call this LUF. I can't even. LUF is literally full spelled backwards.
Oh. That's weird.
Anyway, so I call this wide. I'm not attacking you personally, Dave. Don't worry. You just. Okay, right? Isn't that crazy? It's crazy. So I'm sorry, that was English language. It's incorrect. Okay. Deep breaths. Deep breath.
No.
Okay. So I have a wide subcategory of finite G sets. So it contains all the objects. It's finite coproduct complete, which basically just means that it's closed under disjoint union, it's closed under fold maps. And then, so I can think about it as I took some collection of maps between orbits and closed that up under the finite coproduct completion thing. And the trickier part is it's pullback stable. In this case, that means if you give me an arbitrary morphism in finite G sets as my horizontal leg, and my vertical leg is something in fin GO, then when I pull back the thing in fin GO, that's also in fin GO. A consequence of pullback stability is that fin GO is automatically closed under all the isomorphisms. It has all those. And then the finite coproduct complete in all these, it contains all of the monomorphisms. It's actually a fairly robust setup. Now, there's a poset of these given by the fact that these are all subcategories of the same subcategory. And so those are ordered by inclusion, one inside the next. And that gives me a poset. That poset is the same poset as transfer systems, is the same poset as indexing systems. So it's just another way to rewrite the exact same data that I saw combinatorially. This one, the pullback stability is kind of the key part here. This one lets me define a version of the linear category where I'm gonna, again, make the exact same definition I did before, but I'm going to ask that my map here be restricted to the fin GO as opposed to an arbitrary map. The wrong way map, the backwards map, that one is allowed to be an arbitrary map of finite G sets. The forward one I restrict to fin GO. This is still, it's still the case that disjoint union is both the coproduct and the product. And this is using the sort of coproduct complete. The fact that this gives me a category when I compose again by a pullback is the statement that fin GO is pullback stable. And the fact that I have like nice commutative monoids, all of that is the finite coproduct complete. So it's sort of the things that I would quote there. Yeah.
For fin GO, you take admissible sets here, or you take an arbitrary like indexing category?
So you the O here, I'm sorry, could you repeat that?
It looks like it depends on O.
It does. It does.
So what do you take? You take the admissible.
So you give me an O, by which I would mean like an N infinity operad, or equivalently a transfer system, or equivalently an indexing system. Associated to that is an indexing category, and that's the same, it's the same O.
Yeah, but that's like the indexing category. What's the category of admissible? Okay.
It's built out of the admissibles. Excuse me. That the way I would translate from the admissible sets into this is that I could ask, what are the things that map to some G mod H? And the things that map to G mod H are you induce up the admissible H sets. And so the things that map to point are induce up, or actually I don't have to induce, I just take all the admissible G sets. And it turns out that's describing for me exactly a category that has these properties. So that's the one that I'm going to use to build my O linear category.
I'm trying to understand that you're saying that this has all isomorphisms, right?
Yeah.
And morphisms in the, let's say, orbit category are like subconjugations.
Yeah.
And so that means it's, I either have a map between like two subgroups or I don't. Because once I have a map, then I have all the maps, right? Because
Yeah. Yep.
it's either.
No, exactly. So that, in fact, in some ways, that's the dictionary that takes this to transfer systems. Because the whole thing becomes one of, I just need to know from these conditions, all I need to know is a map between orbits in there or not? And then that becomes the statement, do I have the comparison in my transfer system between the two corresponding subgroups? And as you said, because in the orbit category, the isomorphisms are all given by conjugation. This is essentially the conjugation condition on this. And then pullback stability is that restriction condition, that if I had a transfer from K to H, and I had a subgroup of H, then K intersect J transfers to J. So it's all of the conditions can be rewritten in the transfer language. And that's how Rubin came upon that transfer systems, and I assume that's how y'all also have this. I know because John was working as a postdoc with me. Okay, so an O Mackey functor is just a product preserving functor out of this O linear category. And if I had any old n infinity operad, then and X is an O algebra, then the homotopy coefficient systems are actually naturally O Mackey functors. So this is recording for me the structure that I want there. Okay, I want to switch to talking about a multiplicative story now. And this one is going to be, I'll be honest, this part is going to be a little technical. And I'll try to make that as pain-free as possible. And so I'm going to start with this like rewriting of the distributive law. Because if you can sort of internalize this, then everything I'm going to say is going to feel really simple. So I want to take the tensor product indexed by, all my sets are going to be finite, by some finite set I of the direct sum indexed by some j of these things. And notice the j here actually doesn't depend on I. That's making my life much easier. In this case, I can rewrite the tensor of the sum as a big direct sum indexed by the set of maps. This is a really ugly way of saying I can write down a matrix. That's actually all I'm doing. I'm writing down a matrix. And this thing, the function I want to think of as my actual matrix with I, and it's, well, I guess columns is the way I normally do matrices, and j rows, and then I pick out something I evaluated I that's telling me something in j, and I just tensor together the corresponding entries. So it's the matrix version of this when I try to undo it. Everything I'm going to talk about for the next, I don't know, 25 minutes, because that's going to get us right when we have to take the photograph, and Tina's going to be really angry with me, is going to be equivariantizing this. And again, remember, one of the first slogans that I had was, anytime I'm doing this, I need to think about allowing the group to act on everything in sight. So the group's going to act on I, the group's going to act on j, the group's going to act on the xij's, and then now this space or this set of maps from I to j also has a g action. And if I just keep that in mind, then you actually know all of the distributive laws that show up in everything that follows, and you just write down the one that you need based on the sum or product you're looking at, and it gives you the right formula. But that's not the way it's normally written. It's normally written with the so-called dependent product. And here, I'm just going to do this. I called this part LCC because this is normally described in the context of locally Cartesian closed categories. So here I have this is actually the data for locally Cartesian closed. It's that I have some category, in this case finite G sets, and then I can consider, given a morphism from S to T in finite G sets, then I have a pullback, which takes me from finite G sets over T, the sliced category, to finite G sets over S. And the LCC part is that this functor actually has both adjoints. The left adjoint is super easy to describe. It's composed with my map. And that's like an easy thing. It's the dependent sum. The right adjoint is harder to describe. It's the dependent product. Sometimes people describe this as you take sections of the fibers over points. And the definition is you take sections of fibers over points. I'll unpack that in a few ways. It's basically you multiply together all of the possible pre-images over your things. But because the dependent product is the right adjoint to the pullback, I have a co-unit of that adjunction, which says that for any morphism in finite G sets, I can first take the dependent product, and then I can pull back, and there's a natural transformation from that to the identity. So this is sometimes called evaluation. Because if I think about the dependent product as sections, then this is exactly giving me, the pullback gave me sections and the things I would evaluate a section on. And there's a natural pairing from sections of something cross things you evaluate sections on to the target of my section. And that's exactly this one. So the key player here are what are called exponential diagrams. And here, the only part that I get to vary is this part. So I have two maps of finite G sets, S prime to S and S to T. Out of S prime to S prime to S, this is in the sliced category over S. So I can apply the dependent product along G, which I wrote as for some reason along along F here. This is just the dependent product of this. So that's given to me. Then here I have a little diagram that I can complete to a pullback. That gave me this one. And this is the pullback of the dependent product. That's the one that has a natural transformation back to the identity. So this is that last piece. So the exponential diagram is built out of just my two morphisms here, or if I think about it as an element in the slice category over S, and a given morphism from S to T, and then I'm just unpacking what that gives me. This is secretly distributivity of addition for this one and multiplication for this one. So it's recording for me how do I rewrite the product of various kinds of additions in terms of additions of various kinds of products. And I'll spend a little bit of time unpacking that. So the key player here is what are called, well, I'm moving towards what are called Tambara functors. Tambara called these TNR functors, and for this reason, that I'm going to build a category. The objects are finite G sets, and the morphisms in this category are little strings, really isomorphism classes, where I have S on one end, T on the other. These are the morphisms from S to T, and then I have a map from U to S, then a map from U to V, and a map from V to T. The way, the reason that category theorists call these polynomials is I should think of my finite sets as indicating for me a collection of variables. And then the map R sub F, the one corresponding to this, is duplicate a bunch of the variables. So like take, it's dealing with the fact that normally I deal with sets of things rather than multi-sets. And so I have some set of variables, now produce a bigger set where I've copied a bunch of those variables. Then G records for me, multiply some subsets of those variables together to produce a new set of things, indexed in case by V. And then lastly, add all of those together. So that's the generic way I would describe a polynomial. I take something, some collection of variables, I add in a bunch of extra copies of them, I multiply subsets of those, and then I add them together. This category, I can build a category out of this where I'm going to basically take the free category with objects finite G sets and then morphisms, the ones generated by symbols T, H, N, G, and R, F as I range over all maps of finite G sets, F, G, and H. And then I'll put in rules that specify how to interchange these. So the first is that the assignment F goes to R sub F is contravariant. The assignment H goes to T sub H is covariant, and G goes to N sub G is also covariant. Second, if I had a pullback diagram, then I can swap R and T, or I can swap R and N according to pullbacks. Or if you prefer, if I ignored one of the three classes of maps of the T, N, and R, so I just consider, say, R and T or R and N, it's exactly the data of a Mackey functor that I described. I had the wrong way maps, R's, the right way maps, the T's or the N's, and they have this pullback condition, which is sometimes called either the double coset or you'll also see sometimes Beck-Chevrolet. And then the last part involves the exponential diagram. This is how do I swap a t and an h if I had them in the wrong order. And it's exactly saying I want to transfer, which is where we're summing up along h and then multiplying along g, and I rewrite that as first I duplicate a bunch of variables, then I multiply along the pullback of g, and then I sum up in this case. So this is what makes these a little more. In polynomials, the disjoint union is both again the categorical product. It's actually not the coproduct anymore, so this is something wrong. It's still the categorical product. And then in this case, I can build a product preserving functor out of this into sets, and these are called PNR or Tambara functors. Again, these are really the semi version in that the value of this on any orbit, which all I need to tell you is the values on orbits because the disjoint union decomposition, the value on orbits is always a semi-ring. So this is a ring without an inverse. And then if you give me a map of orbits, then the restriction is a map of semi-rings. The transfer is a map of modules over the corresponding, just map modules. And then the last piece of data is the norm maps, the n sub this map here. And that gives me a multiplicative map that's not additive and has a really confusing interchange with the addition. But we can reduce down pretty quickly using some key features, because the last compatibility condition is how do I understand the interaction between the norm and the sum and the transfers? And the way I can understand that is exactly this. This is telling me what's the norm do to a transfer of something, or what's the norm do to a sum. And now for that, I'm going to break up my exponential diagram to a series of reductions. And this is why you see this definition, and it feels daunting. And it feels, maybe I'll speak for myself rather than sort of in the abstract. It felt daunting, and it felt like, how the fuck do I work with this? Like, there's too many, I told you you'd have to edit a lot. There's too many pieces that are really confusing to sort of describe the structure. I feel more comfortable with, say, more pedestrian objects like a ring or a ring with maps between them. How do I understand it in the same way? And it turns out that the exponential diagram, it's packaging a lot, but I can rewrite it in much simpler ways. The first of which is disjoint union has this disjunctive feature that if I map an orbit into a disjoint union, it lands in one of the two pieces. It never smears across different orbits. So that means when I work one orbit at a time, if I had an exponential diagram where that bottom right corner was a disjoint union, that whole diagram breaks up into a disjoint union of exponential diagrams where that bottom right corner was a single orbit. And so that means I could have just had the case that the bottom right corner in my exponential diagram was an orbit G mod H. On the other hand, if my orbit is G mod H, any map to G mod H is isomorphic to the map G cross the fiber over the identity coset, mapping down to G mod H. So maps to G mod H is also really simple. They're the same as H equivariant maps from the fiber over H. So then if my bottom right corner were G mod H, I can view the entire diagram as being induced up from an H equivariant diagram where the bottom right corner is a point. So understanding exponential diagrams in general is the same thing as understanding exponential diagrams where the bottom right corner is a point. Okay, here, the dependent product is super easy. The dependent product along the fold map, so if you gave me a map from S disjoint union T to point disjoint union point, and it's not obvious from the way I wrote it, but like S maps to one of the points, and T maps to the other point. So this is like a disjoint union of two maps to point disjoint union point. And then that's what I wanna transfer along. And then I want to fold along the map point disunion point to point. So the norm along point disunion point to point is the multiplication. So this is saying, take some transfer associated to S and a transfer associated to T, and then multiply those two together. The dependent product here is the Cartesian product. That's it. It's a pretty familiar object. And in the other case, if I had G mod H going to point and then some set over G mod H, then the dependent product is just co-induction. So since any map to point can be written as a composite of things like this and things like this, that actually tells you how to write the dependent product of any map down to point. And so it tells you how to rewrite any exponential diagram. It's just these, the product and then co-induction. And so that tells you, in a fairly straightforward way, how to actually write down anything like this. So the norm of the sum for just the group C2 is the sum of the norms plus some transfer term.
So how do you decompose this map HGS into orbits? The good way to do that?
Pardon me?
So I mean, if we written the second dependent product as maps from G to S,
Yeah.
how do you break that up into orbits?
What's your favorite way to?
I don't know, is there like a formula for how this thing?
For a general set, there isn't going to be a formula for how I break it into orbits. But it's whatever I'm going to end up using. So if I know what S is, then I do have to analyze it. So there is a little bit of sleight of hand in saying that I do, but I turn the problem of computing the dependent product into exactly that. This is an explicit G set that I want to write as orbits. And then on the one hand, one way to do it is just like, I know what I write down a collection of the functions. And then I know how does the group act because it permutes the inputs. And that tells me how to understand the decomposition. But in general, it gets big really fast. Yeah. Well, I have no idea how much time I have left. So what I want to do is in the, 20 minutes or so remaining, introduce a variant of this because I could have played the exact same game now where I restrict what things I'm allowed to norm along. That would give me the incomplete Tambara functors, but in the interest of time, I'll skip the slides that I didn't make going through that and focus on just doing both at once. So I'm going to allow myself to vary both the multiplicative structure and the additive one. So I'm only going to allow transfers along some transfer system OA, the A for additive. And I'm going to allow the norms to vary along a transfer system OM for multiplicative. And I'm going to say, when I write this expression down, what I've actually written down is a subgraph of the category of polynomials. It's not guaranteed that this is closed under composition. And so I'm just going to say that my pair OA-OM is compatible if in fact it is closed under composition, that I've written down a subcategory of the category of polynomials. And if it's compatible, then I can talk about what I would call a bi-incomplete Tambara functor. It's a product preserving functor out of this into set. So the prototypical example is if you give me anything that I want to use for OM, and I take the transfer system that is the subgroup lattice itself with inclusion, this is the terminal object in the post-set transfer systems, those are always compatible. And that's the incomplete Tambara functors. So Blumberg and I defined and studied these, and we showed that a pair is compatible is basically a condition on closure under co-induction. The indexing system formulation of just an indexing system was a closure under induction. It said that H crossover K preserved the indexing system. The multiplicative compatibility is one for instead co-induction. And then this was enough, this is enough for us, but it was really hard to work with in practice. If your group is abelian, then it's not hard to do because all the subgroups are normal, and so it's fairly straightforward to work this out. If your group is, well, if all the subgroups are always normal, then that's what you really used. But then beyond this, it's hard to make sense of, because it turns out there are groups that are not abelian and that have non-normal subgroups. I know, allegedly. And so that made it really hard to work with. And then David Chan found this beautiful reformulation entirely in terms of transfer systems, where I have the compatibility can be rewritten as saying I have OM for my top and bottom maps, and then OA for my left map, that forces the right map to also be in OA. And so that's the only thing I have to check for compatibility. Once I know that, then I know the whole. You know what? Let's stop here.
You introduced match counter.
Yeah.
And one thing that I'm having trouble like guessing on my own is how restrictive it is to be a acupuncture. And so maybe like one way to ask this question, is there any sense of how big the category of acupunctures for a given group is?
What do you mean by big?
Heuristics, like as in, do you expect there to be many, many different acupunctures, or are there generally 7?
So in general, it's gonna pretty faithfully contain the Z-adjoin file group modules for any subgroup. So it contains like modules of the group ring for the whole thing. It contains all appealing groups because it's pretty big. And then John showed that generically, if I consider from a homological algebra perspective, generically it has infinite projective dimension. So both from there's a lot of them. It can be like hard to understand just from that perspective. And if I want to actually try and compute any sort of homotypically meaningful functors, there's a lot in that perspective. So it's pretty big.
Other questions? Okay, let's thank Mike again.